Welcome back to electronics. This is Dr. Ferry. In this lesson, we will Welcome back to electronics. This is Dr. Ferry. In this lesson, we will cover basic op-amp amplifier configurations. In our previous lessons, we looked at the op-amp ideal behavior and a simple circuit that was a buffer circuit. Now we're going to get a little bit more complicated with it. And we wanted to introduce some very useful circuits, inverting and non-inverting configurations, difference in summing configurations. And we want to introduce the idea of a gain of a circuit. Let's start with a non-inverting amplifier. On the left, it's actually, both of these circuits are the same way of representing it. I wanted to show them both because you might see them both in different configurations. Over here, we show it as a power supply coming in. So power supply, this is level right here, voltage is Vn. And over here, I just show it as a voltage Vn. And the reason that I want to show it in this configuration, sometimes we use this to amplify something say from a sensor. And the input might be coming from a sensor input. So it's not really a power supply. So again, both of these are equivalent sort of configurations, and we use them, the analysis is the same. So here is the equation for it, is right here, the relationship between the Vin and Vout, and I'd like to go ahead and derive that. All right, to derive an equation like that, I want to go back to the basics, which is the ideal op-amp assumptions, and that is that I've got 0 amps going in and 0 volts across the terminals right there. So if I've got 0, let's see, in this particular case, if I've got 0 voltage drop, the voltage right here is the same as the one up here. And if I've got 0 amps right here, that means that there's 0 voltage drop across this right here. And if there's 0 voltage drop right there, then that means that this level is Vn. Because I have have a Vin over here and 0 change of potential, so that means this is Vin right here. And with 0, that means that is also Vn right here, coming around here, that is Vn. At this point in time, I can use a voltage divider law. So if this is from 0 up to Vn, I'm looking at this potential versus that potential. So the voltage divider law with regard to Vin and Vout is simply equal to Vn is equal to R3 over R2 plus R3 times Vout. And if instead I solve for Vout, I get this expression right here. Now I've defined a couple of things here. Gain is an important concept. It's the gain of the circuit. It's a relationship between the input voltage and the output voltage. In this particular case, the gain is R2 plus R3 over R3. Let's look at an example of a non-inverting amplifier. In this particular case, I have particular numbers in there. So the gain is R2 plus R3 over R3. In this particular case, we've got is equal to 400 over 200, so the gain is 2. That means that my output is equal to twice the input level. So if the input is a sine wave with an amplitude of 1, the output is a sine wave with an amplitude of 2. Since the gain is greater than 1, we say that the output is amplified. Gain greater than 1, again, means amplified. So this now is a different configuration. It's an inverting amplifier. The reason we call it inverting is because I've got a negative sign in here. So I want to do the same thing we did last time to be able to derive this input-output relationship by going back to these assumptions. So with the assumptions, again, I have 0 current going in and 0 voltage drop here. Since this is ground, that's 0 volts, and this voltage drop is 0. So again, this is 0 right here. So at this point, I can do a KCL at this node right here. And I'll be looking at, say, how about the current going into the node? Current going into the node. Since that's 0 potential, 0 right there, I've got Vn over R1 is equal to Vout over RF. And from that, I can get this equation right there. And again, the gain is defined as being the relationship between the input and the output. And it's inverting because of that minus sign. So if input is positive, the output's going to be negative. Let's look at an example of an inverting amplifier, again with numbers. So we've got the gain is equal to minus RF over R1, and in this case we've got 2,000 over 1,000 with that minus sign in there, so the gain is minus 2. And in this particular case, we say if the gain is greater than 1, I'm going to go ahead and change that to say the magnitude of the gain is greater than 1, then we say the input is amplified. And again, if this is 2 volts, the magnitude of the output will be 4 volts. Again, it's inverted, so it would be minus 4 volts, but the magnitude is amplified. And if G is less than 1, the magnitude of G is less than 1, then the input is attenuated. So if this is 2 volts and the gain was a half, then the output would be 1 volt. A difference circuit is one that looks at the difference between the two input circuits and multiplies it by gain to give you the output. So this is the input-output relationship there. Now let's go ahead and derive this. Okay, going back to my basic assumptions again, let's see, if this is 0 current going through here, all the current goes through this way. That means that I can use a voltage divider law to find out what this voltage is. And I'm going to call that voltage, say, V sub A. V sub A is equal to RF over RF plus R1 times V2. Okay, and because there's a 0 voltage drop here, this is also VA, right there. Everything on this node is V sub A, which I know what V sub A is now. And at this point, I can do a Kirchhoff's current law here, and I can go, for example, in this direction in the current. Since there's 0 current going through here, the currents have to match between these two branches. So with the KCL at that upper branch, the input terminal, I have VA minus V1 over R1 plus VA minus V out over RF has to equal 0. Now from this equation, I have, let's see, let me pull out my VA. VA 1 over R1 plus 1 over RF is equal to V1 over R1 plus V0 over RF. And let's see, I'm going to write that as, I'm going to substitute in right here for the VA. I've got RF over RF plus R1 times V2. And this term right here, I'm just going to combine my denominator terms, find a common denominator, and I'll have R1 plus RF over the product is equal to the right-hand side. And here I can cancel some terms. And what I'm left with is V2 over R1 minus V1 over R1 is equal to V out over RF. And from that, it's pretty clear that I can derive this expression right here. So in this particular case, the gain is equal to RF over R1, and it's the gain times the difference between the two voltages. A summing amplifier, very similar to a difference amplifier, except of course we're summing the two signals. So in this case, going back to these same assumptions, I've got 0 volts here, that means there's 0 volts here. That means that I can do a KCL. Looking at these currents, I'll have to add up together to get 0. And again, there's 0 current going in this way. So these 3 current branches right there. So I've got, let's see, since that's 0, let me look at it actually as the current going into those nodes rather than the current going out. KCL, the current going into the node would be V1 over R1 plus V2 over R2 plus V0 over RF has to equal 0. And if I clean this up a little bit, I can see that I can put it into this form. So I've got actually 2 gains, G1 times V1 and G2 times V2, and they're a little bit different in terms of their values. And you can see that both the difference circuit and the summing circuit, well, actually in the summing circuit, I can add more terms in here. And I can do the same thing that I did here if I had 3 inputs, 4 inputs, or whatever. I can sum them all together. So in summary, we've defined a gain, which is the multiplier of the input voltage to give us the output voltage. We went through some basic circuit configurations, the non-inverting, inverting amplifiers, and the difference in the summing amplifiers. These are really, really common and very useful circuits, and we use them a lot of times when we're
Hola, ahora esta parte de aquí, si V2 va a ser puesta a cero, así que eso en realidad lo mismo que ponerlo a más. Entonces, eso sí significa que hay cero corriente que fluye a través de R1 o RF. Y con cero corriente allí, entonces esto de aquí es equivalente a tierra, pero puedes simplemente conectar eso a tierra porque tiene el mismo potencial de tierra. En ese caso, esto se ve exactamente como un amplificador inversor.
looking at sensors and we want to amplify the sensors, or we want to compare two sensor readings or do some processing like that. And the other time that it's useful is the output of, say, something like a microcontroller, where we want to do something with the output to before we're putting in, we want to amplify it, for example, before we're putting it into a motor or some other device that we're trying to drive. All right, thank you.
Lo que me falta. Yo no sé cómo haces esto. Vamos a pedir ayuda. Ayuda a un amigo. Como que está buena, ¿no? Para el circuito amplificador operacional inversor anterior, sí. R es igual a 2. R de entrada es igual a 2 kiloohmios y la ganancia del bucle cerrado debe ser G igual a menos 40. ¿Cuál es el valor apropiado que se debe elegir para la resistencia RF? Pues es supuesta. Entonces, tengo G. G es igual a RF sobre R, RI. Entonces, tengo G, tengo RI, pero no tengo RF, solo espejo. RF es igual a 40 por 2000 ohmios, igual a 8000, 80.000. Está correcto. Continuemos. Ganancia es igual a RF dividido por RI. Ujú. Otra tarea. Para esta pregunta, 5 kilo ohm, 10 kilo ohm, 10 voltios y 12 voltios son tensiones en los nodos R1, RF, BI, B1, B2, B1, B2, B0. ¿Cuál es de su respuesta en voltios y omita las unidades de su respuesta del voltaje de salida? Pues tengo RI, R1. Uy, pero acá falta algo. ¿Qué? ¿Por qué se ve así? R1 es 5, RF es 10, 10 y 12 voltios. Entonces se hace así. Eso se coloca. Voltaje es igual a 4. Error. Es menos 4. Lo que es 4 positivo. Entonces debe ser 4 positivo. Si se trata de un amplificador diferencial. Ahí está la fórmula. RF sobre RI por B2 menos BI. Se reemplaza y ya. Y da 4. 4. ¿Qué es esto? Vean, dice la figura anterior, un K, 2 kiloohmios, 3 kiloohmios. Las fuentes de alimentación para el OPAN son 15 voltios y menos 15. ¿Cuál es el valor de? ¿Cuál es el valor de? Tengo R1, tengo todos R y los voltajes, solo reemplazar en la fórmula, justamente a 15. Se trata de un circuito vera- veraniego inverso. Circuito amplificador inversor. El voltaje de salida calculado es mayor que 15, por lo que se produce saturación y es igual al voltaje de la fuente de alimentación de 15 voltios B0. Entonces, B0 es igual a menos 12K por, son los 12K que tengo acá, por paréntesis, menos 4 sobre 1K, más 2 sobre 2K, más 1 sobre 3K. Resuelvo esto y me da 20 voltios. Pero el OPAN satura a más 15 y menos 15, así que respuesta final considerando saturación 15 voltios. O sea que me dio un voltaje más grande, entonces, claro, el OPAN no lo permite. ¿A qué debe cambiarse para que sea de 13 voltios? Su respuesta de kiloohm sin unidades. Uy, ¿cómo así? ¿A qué debe cambiarse? ¿A qué debe cambiarse? Pues si yo quiero 13 voltios en vez de 13 voltios de salida, la resistencia debe ser, dice, debe su respuesta en kiloohmios sin unidades. Vamos a ver si es esta. Dice, acá está, menos 12 sobre RI por menos 4 más menos 12 sobre 2 por 2 más menos 12. Bueno, me pregunta qué resistencia debo cambiar para que me salgan 13 voltios. Entonces, no, me dice que la resistencia de entrada, o sea que es menos 4, o sea que es así. Menos 13 va a ser igual a menos 12 por, para paréntesis, menos 4 sobre RA, más 2 sobre 2, más 1 sobre 3. Entonces, que tengo que despejar ahí? RA. RA tengo que despejar. Entonces, sumo 2 sobre 2 más un tercio. Eso me da 4 tercios. Ahora sí quiero sacar esa RA de ahí. Rompo paréntesis, multiplico. Paso, el menos 2 está multiplicando, paso a dividir. Y ya, y despejo RA y me da esto. De acuerdo, está complejito, ¿no?
Welcome back to Electronics. This is Dr. Ferry.
Soy la doctora Harvey.
In this lesson, we'll be covering differentiators and integrator circuits. In our previous lesson, we looked at basic op-amp amplifier configurations, and those configurations in those circuits, we use just straight resistors. In this case, we're going to introduce capacitors, and by doing that, we're able to create circuits that differentiate or integrate the input. We'll also demonstrate the performance of these sorts of circuits using an oscilloscope on a real circuit. Let's start with the differentiator circuit. In this circuit, everything is based on the IV characteristics of a capacitor. I is equal to C dVc dt. We're also going to use the ideal characteristics of an ideal diode, which is zero current, an ideal op-amp, zero going into these two terminals, and then the voltage drop across here is zero. So let me go through and do a KVL around this right here, going up through this source, across the capacitor, through the resistor, and back out to here. And I'm going to treat this as being a voltage drop like this. So actually I go straight back down to the ground right here. So the KVL. Well, let's see. One thing that I can look at actually to simplify this, I'm going to do two KVLs. Let me do this first one, this one right here first.
Las mallas.
In this particular one, this voltage drop is zero, and this is the ground. So this actually is the ground right here. This is equal to zero potential. That means that Vn is equal to the voltage across that capacitor. And we'll define the current as going in this direction, so that voltage drop is plus minus V sub C. Now my second KVL is around this outer loop right here, and writing that I get minus Vn plus V sub C plus R times I, because all the current going through that capacitor must go in this direction, since this current is zero in this little branch there. Plus V0 is equal to 0. Now this first equation still holds. In other words, these are equal. That means that this cancels out. And what I'm left with is V0 is equal to minus R times I. Well, I is up here, C dVc dt. Well, V sub C is equal to Vn. So that's where we get this equation right here. So this is now the equation that governs this circuit.
Dice más voltaje más VCC, más el voltaje del capacitor, más la resistencia por I, más el voltaje de salida, igual a 0. ¿Okay?
The differentiator circuit. I want to show you an example of a real circuit that we've built to demonstrate this.
Un microfaradio y un K.
And we're using a real op-amp chip right here. And that op-amp chip has 8 pins to it. And if you can look carefully right here, there's a little indent right up here. And where those indents are, that shows you that the one pin is going to be just to the left of it. It gives you the orientation. And there's a 1 pin, 2, 3, 4, 5, 6, 7, and 8. That's how I know how to hook things up. In the 2 pin, we're going to be hooking up to V minus. Well, V minus is right here. So let me show that as a 2 pin right here. Where is that over here? Well, the indent is right here, so the 2 pin is right there. We count 1, 2, and that's V minus. So actually, let's start looking at this circuit right from the beginning. So we've got V in goes into the capacitor. So V in comes in, that's from my function generator, goes into one side of the capacitor. The other end of the capacitor goes into V minus, which is right there, the 2 pin. The capacitor also goes into the resistor, and the resistor is connected over to V sub 0. So V sub 0 is a 6 pin. I'm going to mark it as a 6 right there. So we should have a resistor going between the 2 pin and the 6 pin. So that's the 2 pin there, and there's a 6. So that's 1, 2, 3, 4, 5, 6. So that's the 6 pin right there. And that is connected to V0. Now, the voltage source to power this, we've got minus 15 volts connected to pin 4 and plus 15 volts connected to pin 7. We can see V sub S here and minus V sub S there. So this is now my circuit that implements this schematic. Let's look at the results here for the oscilloscope. If Vn is this voltage right there, and V out is this voltage. So if we look at this voltage here, V out and Vn. So it does differentiate. If Vn is a triangular wave, then if I take the derivative of it, I get a constant. And I'm actually going to get a positive constant, but then I negate it. So that's why it goes this way. So my output is equal to the derivative of the input. And I have a scaling factor in there, a gain, which is equal to minus RC. And that's whatever I pick. So I design my circuit with a particular value of RC in mind.
Dice, para el circuito diferenciador que se muestra a continuación con una entrada de 2T voltios, seleccione la salida más adecuada de 2T voltios. Pues si es un comparador, más adecuada. Dice menos voltaje, no. Está entrado por el lado inversor, una resistencia, y el no inversor está el positivo. No sé. Fotogramas. Marquemos mal. ¿Será que la invierte negativamente? Pues si es un inversor, sí, ¿no? Sí, la invierte. Si se, am- si se amplía, si se aplica una onda triangular, y si se aplica una onda triangular a la entrada de un diferenciador, ¿cuál será la forma de onda de salida? Una onda de salida, una onda cuadrada, una onda cuadrada, una onda triangular, sinusoidal, con pendiente, una onda triangular. Está bien.
Now let's take a look at the integrator circuit. The integrator circuit again uses the IV characteristics of a capacitor. But this time, we're going to integrate this equation and get the integral form of the IV characteristics here. And that's what we'll exploit. So this circuit has a switch in it. And the switch opens at time equals 0.
Ay, sabe que no active. No, si está activado. Pensé que no estaba activado.
So prior to time equals 0, we have a closed circuit right here. We short out the capacitor. So for t less than 0, we want to write the equation. In that case, we can look at a KVL around here. And around here, we're going to use this ideal op-amp characteristic, which is 0 volts right there. So that means if that's 0 volts, and I've got a current I that we'll define as going through this resistor, that resistor or that voltage across this resistor has to equal Vn. So Vn is equal to I times R. And also, I can do another KVL around this outer part, up through this voltage source, across this resistor, up through this, which is closed before time equals 0, and back down to here. And I'll do the same thing that I've done before just to emphasize the fact that I can finish this loop right here back down to ground. And if I do that loop, I get minus Vn plus IR plus V0 is equal to 0. Well, since Vn is equal to IR, these two cancel, and I'm left with V0 is equal to 0. Now, for t greater than 0, the capacitor is now in the loop. So I can write a KVL going across that capacitor. I'm going to get the same minus Vn plus IR. Now I have to go through the capacitor, and that capacitor is, voltage is, I'll call it V sub C, plus V0 is equal to 0. Well, let me substitute in. Again, this part cancels out, and let me substitute in for V0 from here. So we get 1 over C, the integral from 0 to t of I dt is equal to minus V0. Well, I is equal to, we can solve from up here, I is equal to Vn over R. If I substitute that in for I, I'm going to get this equation right here. So this is the equation of this line where I take the input, I integrate it, I multiply it by a gain factor, and I get my output. Let's look at an integrator example. This is exactly like what we did before. The only thing different is I've switched these two components around. With the differentiator, we had the capacitor here, now we've got it over here. So I've just switched these two around. And similarly, I've taken this circuit and I've just switched the resistor and the capacitor around, and everything else is the same. So if I look at my results now, Vn is right here, and Vout is right here, and I'm integrating Vin to give me Vout. And I do have a little bit of clipping right here because it goes out of range. Remember, capacitors, or the op-amps will saturate when the... Welcome back to Electronics. Switch I am implementing this equation with this circuit.
Se saturan cuando y queda esta pregunta. Si la entrada de un integrador es una onda cuadrada, ¿cuál será la forma de onda sinusoidal? Si la entrada a un integrador es una onda cuadrada, pues una sinusoidal, ¿no? Pues que no. Una onda triangular, diente de sierra. No sé. Mucho me toca consultar. Si la entrada a un integrador es una onda cuadrada, una onda triangular. O sea, de la cuadrada pasa a una onda triangular. Una onda triangular.
In summary, we have looked at differentiator and integrator op-amp circuits, and we come up with these two equations, these input-output equations for these two circuits. One is the differentiator and the other is the integrator. And I might mention that these two circuits were very important to early analog computers. Early analog computers, they used differentiators and integrators, and they used op-amps all through those computers in order to be able to do two things. One was integrate and differentiate values, and the other thing was to provide gain. So old analog computers full of op-amp circuits. In our next lesson, we will do active filters. Thank you. Welcome back to electronics. This is Dr. Ferry.
Sí. Siguiente. No acabo el 2, me falta el 3. Ve, mira eso tan largo. Eso está larguísimo.